So looking at properties of logarithms, we will use these to condense or expand logarithmic expression, which will definitely come in handy, especially the condensing when we look at actually solving logarithmic equations. There are a bunch of different properties for logarithms, but many of them we don't have to memorize if we just understand how to evaluate a logarithm. So I'm just going to look at the basics and how to evaluate, and then you'll be good to go. So properties of logarithms. So the first one, let's say that I have log base 7 of x plus log base 7 of y. So things to notice here. Both logarithms, or however many logarithms I have, I just wrote 2, but this isn't restricted to just 2. I could have 50 logarithms. As long as they all have the same base, so notice both of these have a base of 7, and all of the logarithms are being added together, then I can condense these logarithms into a single logarithm by multiplying the arguments. So x times y gives me x, y. So there's our first property. This property works both ways, to condense addition into multiplication, and then likewise if I for some reason needed to expand the logarithms, if I have a logarithm with multiplication on the inside, then everything that is being multiplied can be separated into its own logarithm, separating the logarithms by addition. So let's say I have log of x, y, z. Let me throw a little 2 in there. There we go. That's a z. So notice here I have 1, 2, 3, 4 things being multiplied. I don't appear to have a base. Hopefully you recognize this as the common logarithm with a base of 10. But so I have 4 things multiplied, which means that I can expand this logarithm into 4 separate logarithms, each logarithm with an argument of each of these values, all of them being separated with addition. So I could write this as log of 2 plus log of x plus log of y plus log of z. There we go. So it does work both ways, expanding and condensing. So there's our first property of logarithms. We also have, so this is the addition multiplication property, we also have a subtraction division property that says essentially the same thing except with subtraction and division. So let's say that I have, I don't know, log base 2 of x minus log base 2 of y. So again, important things to notice, the bases are the same, and the subtraction is occurring between 2 logarithms. The subtraction is not on the inside. We do not have a property for subtraction on the inside of the logarithm. It's only when 2 logarithms or more are being subtracted themselves. Then I can condense those logarithms into a single logarithm by dividing the argument. So log base 2 of the first divided by the second, so x divided by y. Important thing to note here, the logarithm that was being subtracted ended up, that argument ended up being on the bottom. The logarithm that was initially positive ended up being on the top. So if addition and subtraction was combined together, then all the all the arguments that were in logarithms that were being subtracted would end up being multiplied in the denominator, and all the positive logarithms, their arguments would be multiplied together in the numerator. So let me show you an example of that real quick. Alright, so let's say I have this real quick right here, log of x minus log of 7 plus log of 4 minus log of y. And I wanted to condense this down into a single logarithm. So I have addition and I have subtraction. The subtracted logarithms, we could do this the long way, rewrite them together, and factor out that negative. If we factored out the negative, we would see that they are technically being added together with a negative on the outside, which means they should be multiplied since they're added, but then in the numerator since it's subtraction. So long story short, if they are subtracted, those arguments will be multiplied together in the denominator. The ones that are originally positive will be multiplied together in the numerator. So this expression condensed down into a single logarithm would be log of my positive logarithms have arguments 4 and x, so those will be multiplied together on top, 4 times x. And the negative logarithms, those arguments will be multiplied together in the denominator. So 7 times y gives me 7y. So there we go. Alright, so the third property we need to look at is the power coefficient property and see where does that come from. So let's say I have log of x squared. So this one deals with just a single logarithm. What this property tells me is if I have an argument that has an exponent, that exponent can be pulled out as a coefficient, and likewise if there's a coefficient, it can be pulled in as an exponent. So again, an invaluable property to have when we go into solving these logarithmic equations. I do want to show you why this one is true real quick. So log of x squared means x times x. And now since there's multiplication inside this logarithm, I can use that first property that we looked at to separate that multiplication into two different logarithms being added together. So I'm going to rewrite this as log of x plus log of x. Now how many log of x's do I have? I got 2 of them. Which shows what the property tells us, that I can take that exponent and just pull it out as a coefficient. So now that you understand that property, you don't have to go through the long way, you just know you can pull that exponent out. Do be careful with it though. That exponent needs to be fully on the argument before you can pull it out. What do I mean by that? Let's say I have the natural log of x to the 5th times y squared. Now, I have a single argument, but not both things are being raised to the same exponent. So before I can pull these exponents out, I have to separate them. So this is multiplication, so I can rewrite this as the natural log of x to the 5th plus the natural log of y squared. Now inside each argument, the whole argument is being raised to a power, so I can pull that power out as a coefficient. So just be mindful of that. Alright, the other properties are, like I said, very handy properties, but you don't have to memorize them as long as you understand how to evaluate a logarithm. So things like log base b of b is equal to 1. Now, what does that say? If you recall how to evaluate logarithms, if I have log base 3 of 3, to evaluate that, remember that the logarithms are the inverse of the exponential. So I'm just going to think of this in the exponential sense. 3 to what power gives me 3? Well, 3 to the first power gives me 3. This is true of any positive number. Yeah. So this property just says that in general. If your base and your argument are the same, then that exponent has to be 1. They take it a step further in the properties, tell you log base b of b to the nth power would be equal to what? So I'm not going to write it down for just a second. Think about that. B to what power gives me b to the nth power? The answer would have to be n, and you're going to see that a lot with things like this, the natural log of e to the fifth. Evaluate it without a calculator. It looks scary, but if you recall, the natural log is just a logarithm with a base of e, so this is just asking you e to what power gives you e to the fifth power, and that answer is 5, so it just simplifies. Alright, the last, it's not really a property, of logarithms that we're going to look at is the change of base formula. So, in general, most calculators are only equipped to handle the common logarithm, so just the regular log, and the natural logarithm, so Ln. And if you need to evaluate something that has a base other than 10 or e, you need a way to convert. So what the change of base formula says is if you have log base a of b, I can rewrite this as, I always have to derive it because I don't ever remember what it is, so let me rewrite this real quick. Alright, so what the change of base formula says, I just derived it. I didn't write it out, but it's a good exercise to think about. So the change of base formula tells us that if I have log base a of b, I can rewrite this, I use the natural log, I can rewrite this as the natural log of b divided by the natural log of a, or if you so choose, you can use the regular common logarithm, so log of b divided by log of a. Either one will get you the same exact answer. So let's do one with numbers real quick. Let's say that I need to evaluate log base 2 of 7. Now, what that is asking you for is 2 to what power gives me 7. There's some number, I just don't know what it is. It's not a pretty number, right? If this were log base 2 of 8, then my answer would be 3, because 2 to the third power is 8. But since I got 7, that's not the case. So I would need a calculator to evaluate this. My calculator is not fancy. It does not have the option for a base other than 10 or e, and this is a base of 2. So I do need to use the change of base formula. And the change of base formula tells me it's the natural log of b over the natural log of a, or log of b over log of a. I'm partial to the natural log for some reason, so I'm going to use the natural log. My b, in this case, is 7, so this is the natural log of 7 divided by the natural log of 2. My calculator can absolutely handle the natural log. So I'm going to grab my calculator real quick. The natural log of 7. And again, be very careful with your calculator. My calculator, let me show you. You can see that. Yeah, so the natural log of 7, it opens the parentheses, so I need to close the parentheses so it knows I'm done with that argument, and I want to divide that, all of natural log of 7, by the natural log of 2. If you don't close your parentheses, back up real quick. If I did the natural log of 7 divided by the natural log of 2, it's going to think that your argument for the first natural log has this other natural log in it, and that's not what we want to do. So just make sure you close your parentheses. So the natural log of 7 divided by the natural log of 2 gives me this number right here. And I'm going to round to the nearest hundredth. So I get approximately 2.81. But again, just be mindful of what the problem asks you for.